Welcome back, everybody. This is Math 21, Introduction to Statistics at College of the Sequoias. In this section, we're going to look at dispersion or deviation. This is 3.2 in our book. It's on dispersion or deviation. And so what I want you to do, so starting exercise, calculate the mean of each of these groups. Pause the video and calculate the mean for each group, for each set. Set A, we're going to have the numbers 46, 48, 50, 52, 54. And for set B, we've got 10, 30, 50, 70, 90. So calculate the mean or X bar for each set. Now, if you go ahead and pause it and you worked it out, set A, the X bar for set A is 50. And the sample mean or X bar for set B is also 50. Okay? So does the mean paint the whole picture of what's about the data set? Now, if I were talking about grades, and this was your percentage score on the final, set A, every student failed. If it was grades and set B, one student got an A, the 90%, one student got a C, the 70%, and everybody else failed, but two people passed that final. So, but they both have the same mean. So this doesn't paint the whole picture. It doesn't really show how much the data is spread out. It doesn't show how much the data is spread out from the mean. From the center or mean. Okay. That's the idea of dispersion. When we say dispersion, it's a measure of how much spread out the answers are, or how much spread out the data is, or how much it deviates from the mean. Okay. A word we're going to use in this area is the range. The range for a data set is the largest value or greatest value minus the smallest value or least value. And that is a minus sign. Okay, we subtract the smallest value from the largest value. So let's take a look at what the range is for our data set. So in our examples, set A, 46, 48, 50, 52, 54. The range is the largest, which is 54, minus the smallest, which was 46. The range is 8. For set B, 10, 30, 50, 70, 90. The range of B is the largest, which is 90, minus the smallest, which is 10. 90 minus 10 is 80. So the bigger the range, or the greater the range, the more spread out the data is. Or dispersed, the data is. Now, is the range resistant? Remember, we talked about resistant. Resistant statistics are not affected by outliers. If we had set A, and we're talking about math students, and all of a sudden Professor Jones is one of those math students, and you know Professor Jones isn't happy with less than a 98%. In fact, he's not happy when he gets under 100%, to be honest, which happened almost every single time. If I had 100, I'm an outlier here, and I'm definitely throwing off the range. If we added Jones to set A, we added 100. The range is now 100 minus 46, which is 54. 100 was an extreme outlier. The outlier of 100 had a huge impact on the range. Which means the range is not resistant to outliers. Okay. That's one way we measure spread. That's not the best form. That just shows us what our smallest and largest values are, how much we're from the center, kind of thing. A better way of measuring spread. So I'll pause and let you write this down. Okay. We frequently measure spread by standard deviation. That's what we call it. And when we're being lazy, we just say deviation. Okay. And it's different for populations and samples. This value is different for populations and samples. Versus samples. So we use different symbols again. So for a population, I mentioned this in the last section, we use the symbol sigma. It's an O with a really long tail on top. And what it is this is the square root of, you're going to take every single data term, the xi, then you subtract the population mean from it, mu, you square them, you divide by the sample size or the population size, which is capital N, and then you take the square root. Okay? So to do this, you need the data set, the population size, and population mean. And this is the lowercase sigma. So that's lowercase sigma. And as a reminder, N is population size. If we look at a sample, for a sample group, we use S, lowercase s. I don't think I made it look lowercase when I was writing it right there. Rather than scratching this whole page and starting over, let's just pretend that was lowercase. Lowercase s, it's very similar in format. We're still doing the square root. On top, we're going to put xi minus x bar now, each data set minus the mean. We square it. And then we do, and rather than doing just lowercase n, we do n minus 1, where n is the sample size. And n minus 1 is called the degrees of freedom. They found when they did this, using just n did not give a very accurate response for deviation. N minus 1 made it better. And the idea behind it is, if you use the n minus 1, once you're done doing it, and you can use the sample, or you can use the standard deviation to get stuff back, you can get back the original mean when you work stuff out. When it's a lot of math mumbo jumbo, n minus 1 makes this operational, n doesn't. Okay? And this is very much like me holding up, oh, look, I've got 4 pin colors in my hand right now: black, green, red, and blue. And if I offer students A, B, and C, D a pin, well, let's say A picks red first. Now I don't have a red pin. B gets to choose between black, green, and blue. Let's say student B picks black. Student C now only has 2 choices, green or blue. Let's say they choose green. And now student D, the last student, only has B to pick from. That student doesn't have the freedom of choice. They don't get a choice. The choice is selected for them. So that's the idea of like the last one not counting, or n minus 1. That's where the idea comes from. Just remember, n minus 1 equals degrees of freedom. You will see D.F in StatCrunch a lot. If they ask or reference degrees of freedom, you need to deduct or subtract 1 from the sample size. Okay? So, those of you that just saw those equations, I thought, wow, those look pretty rough. Pretty rough to use. And guess what? They are. They are error prone. When calculated by humans. if you got 100 pieces of data, and 100 is not a big sample, believe it or not, you have to calculate the mean, then you got to do each thing, each data entry minus the mean. You're doing that 100 times. Then you're squaring those 100 times. Then you're dividing by n 100 times. Oh, I missed something. We need to add up those things. It's a sigma there. You add up the square of the differences, and then you divide by those things. My bad. So you're doing for a sample size of 100, you're doing 100 subtractions, you're squaring 100 different numbers, you're adding 100 different numbers, then you're going to divide by the sample size, then you're going to take the square root, and guess what? If you make a mistake in any one of those, your answer is wrong. So these are very error prone, which is why we like using computers. Or calculators. Some sophisticated calculators, a lot of sophisticated calculators have stat commands in there. They are a pain to use. You have to go through and manually enter in each one. You got to remember what key configuration is on the calculator, and every calculator is very different. So StatCrunch, we're going to use StatCrunch. And conveniently, it's the same as finding the mean. Same as finding mean. We're going to go to stats, summary stats, columns. We'll do that in a second. Let's do it now. So in my stat lab, remember, scroll down to StatCrunch, select it, click visit the StatCrunch website, which gets you to there. Then either open a new StatCrunch to enter data or open a data set you've already saved. I've got a data set here that I'm going to use. And let's look at we'll look at siblings to illustrate the example. Stats, summary stats, columns. And use siblings. Scroll down here, there's one that says standard deviation or STD.dev. This is for samples. And it's a little different. If you scroll all the way down, you see unadjusted. Wait, crap. So I've got unadjusted and that. The unadjusted or UNADJ.std.dev. This is for populations. We rarely have that. You're usually using the top one. This word variance, we also have unadjusted variance. I'll cover what that means in a second, but let's just take a look at it. Siblings, we calculate the standard deviation. The standard deviation is 2.19. And depending on how many places StatCrunch or the My Math Lab homework wants, you use that many different places. How this relates to variance, I'll just tell you, you do a lot with variance, but you can. And this is an introduction to stats, but if you like pursue stats and do a lot more with it, you'll use a lot of variance as well. Variance is the square of standard deviation. Okay. So for populations, we have sigma squared. And for samples, we have S squared. Okay. A common one that you'll see this on. This is ideal. This formula, or these formulas, work a lot better for bell-shaped distributions. But not so well for skewed. Okay. For skewed data, or for any shape, a formula that works for any shape that's related to this concept is called Chebyshev. 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 It is a fantastic name. I love the name Chebyshev. Chebyshev's inequality. And it works for any shape. For k deviations from the mean, where k is like a variable here, for k deviations from the mean, which means we want k to be greater than 0. We don't want k equals 0. That's useless. We have this information, 1 minus 1 over k squared. We'll do that in parentheses. And then you multiply that by 100%. This is the percentage of the data that is within k deviations. And we don't have k greater than 0 isn't really helpful. We actually want k greater than 1, right? If I put in 1, I got 1 minus 1 is 0. So k greater than 0, that's not right. We want k better with k greater than 1. Okay. And what this will give us is, like, if we take the mean and we subtract k deviations times that value, or sigma, or the standard deviation, and we have mu plus k deviations, then the percentage of the data that's between it is in the middle. Like if you were to make a hump, and here's our center, and we go out, like, let's say k equals 2. We go out 2 deviations from the center, 1 sigma higher, 2 sigma higher, 1 sigma lower, 2 sigma lower. It's the percentage of the data that's underneath the curve. And the rest is outside. A common one that you may have heard of where we use this on is the IQ test. So the IQ test is a common example of this. You can actually take it if you want. It's at Stanford Binet, BINET, test, TEST.com. There is no other, there's no point between Stanford, Binet, those are people. Stanford Binet test.com. This is the average intelligence of the population. Population, or mu, is mu equals 100 with a standard deviation of 15. And we'll do more with this later, but let me just illustrate what's going on pictorially. So if I've got 100 in the center, and I go the same distance either way, I do 100 plus 15 to get this direction, or 1 sigma. I'm at 115. If I subtract 1 sigma, I go left, I subtract 15, I'm down to 85. This region has 68% of the data. 68% of responses are in here. If we go out another deviation, if we add it, make it up to 2 standard deviations, or plus 30, which gives me the 130, or minus 2 deviations, we subtract 30 from 100, we get down to 70. You get down to here, that much. It's about 95% for 2 deviations. Pretty close to it. We use 95% because it's really close to it. And 3 deviations, or we subtract at plus or minus 45, gives us the values from 55 to 145. 99.7% of values or people are in this range. Okay. So a score, what that means is a score of 55 when you're at the bottom is over 99.7% of the population is smarter than you. Almost everyone is smarter than you. If you have an IQ of 145, there is hardly anyone in the entire world smarter than you. Okay? There are exceptions. But again, StatCrunch, we're going to do stats, summary stats, columns. If I looked at the deviation in the age of the class, and I look at the mean, the average age of students in the class was 22 with a standard deviation of 6. Okay. If I add the range in there, range is also available on this stats, summary stats columns. Let's throw median in there to take a peek at it too. The range is 33, which means, what was the highest value and lowest value? Do a histogram of age. There was a student over 50 in the class, and 15 was the youngest student. So there was a good range of students there. The average age, this was a histogram distribution of ages. Notice that it's skewed right. Most values are around that 20 years old. 18 to 22 is the average age of college students, but there are people in their 30s, 40s, and 50s in college. I am tutoring a student right now that is 73 taking Math 11. It's never too late to go back to school. Okay, the student's doing a fantastic job too. So standard deviation is there, means there. We will use this a lot more later on in the class, but this is how we find it. Stats, summary stats, columns. Okay, peace. Close that out and stop the video. Bye.